So quick show of hands. Who here runs their own AI hardware at home? Wow. That is not a lot of people. Kind of expected more from this crowd. That's OK. I know H100s are a little bit pricey. But if you were at HashiCorp last year, we made that joke that Amazon will ship them next day. Yes, it's 30 grand on your credit card, but still, you can run your own models tomorrow. That's great. But first, who are you?
So hi, I'm Scott McAllister. I'm a developer advocate at a company called vCluster. I come from Seattle, Washington, and I just want everyone in this room to know that I love cheeseburgers. Who loves cheeseburgers? Yeah, that's right, and so do I.
This is the right audience for us. Hello everyone, my name is Kerim Satirli. I'm a senior developer advocate at HashiCorp, where I get to build stuff like the RoboRally and infrastructure and orchestration things. If you haven't tried out the RoboRally, quick pitch, you got to go over, use some Terraform to make your robots go around. No AI on there, on purpose, because we don't want to make it too easy.
And just to set the bar, the last time I saw it, the record was 1 minute and 4 seconds. So get the robot through the course in 1 minute and 4 seconds over at the RoboRally.
But we're here to talk about AI.
We are here to talk about AI. We're also here because I love technology. I love the dance between software and hardware and how they come together to create solutions that shape our world and change our lives. But specifically, we're here to talk about how Kubernetes works with GPUs, because that's a different sort of relationship and a different sort of dance. So we're going to jump into a couple of different things here, talking about our clusters, because traditionally, Kubernetes was built to run on CPUs, to run with CPUs and memory, and it had things on the system that it had access to, things like Linux C groups, to keep our access to our different, losing the words, Kerim, for our different resources on our machines. Now, it has a whole different setup where it actually has to go through our GPU driver to actually access that hardware. And when it does that, it's more of on the sidelines. It does basically whatever the driver lets it do. And so today we're going to talk about some ways that you can take that GPU hardware and get the most out of it, because the last time I checked, the price on those things is not low.
It's an investment, that's for sure. You don't do it to just run your own ChatGPT
No,
at home.
not usually.
So unsurprisingly, just like last year, what we're seeing is more and more interest in AI, right? Everything has to have it. Your phone has a couple different things running, both locally and remote. Ollama just introduced Ollama Cloud stuff. You can run anything. You should run some models just to try out things. Shout out to Docling and the new model for multilingual recognition of documents. It's worth it, right? It is a fun area to be in, but there's this little problem that as the interest goes up, as the use cases go up, the demand goes up, the price doesn't come down. If you invested in NVIDIA, this is not investment advice, but you'd have done really well. And you could have probably afforded an H100 at this point.
You could probably afford a couple.
Which is good.
Right.
Which is good. But what do we do with that? So, sorry, there we go.
Yeah. So what we need to do, Kerim, is we need to actually usually we're going to have a situation where it's more than just you using that hardware. You're going to have multiple people on your team. You're going to have multiple teams. Maybe you're in a situation where you provide hardware to customers. You're going to have multiple customers and teams using those GPUs. So I want to talk about a few different philosophies or tactics or ways that you can share your GPUs to kind of set the level straight, kind of essentially let you know what's available in what situations you have. The first is the one you see up here on the screen. This is what's called multi-process service, or MPS. This essentially creates a CUDA context. CUDA is essentially the API or the software layer that NVIDIA provides for you to be able to work with their hardwares, work with their GPUs. And so in this situation, you have a shared CUDA context for all of your different tenants. And then that way, you don't have to have context switching. When you have all the different processes that are going to be reaching out to that GPU hardware, they're going to be going into this one shared space, that shared set of memory, and then it can, the driver won't have to context switch, and so you have a lot less overhead with your processing. Makes it super efficient. It's super nice because you don't have to do anything from the hardware level. However, it is a shared space. So there is a potential, right? There's potential that you could be interacting with other people in there that you may or may not want to be doing.
I don't want to share my GPU.
Not so much.
No.
Yeah.
That's not for me.
So then you have separation on the hardware level. Here, if you're getting a more recent GPU, one of the higher end GPUs, then you're going to be able to use something called MIG, right? So, or multi-instance GPUs. It's done at the hardware level. They're able to essentially partition off segments of that processor so that you can have a specific slice for your processing. So each tenant can have their own, essentially, their own room inside of that GPU. A couple of different gotchas you want to think about. A, it's a fixed slice. It's only a certain size that you can have, and also you can only have 7. Right? The hardware, the way it works, the way it's set up, the way it handles the processing, it can handle 7 partitions there on MIGs.
So we need 5 more friends. Is what you're saying.
Yeah,
Got
exactly.
It. It's kind of like time slicing. Like you buy a timeshare, you get to take some time there. The principle is the same. It works the same. It's cool, but it also feels very much like the 1960s where you got computer time that your university provided with you to you. I say this as if I had been around back then. I'm not that old. But we've read about this.
In history books.
History books,
or
yes.
Maybe
when bugs were actual bugs in the machine. And of course, anytime you get something that's time-based, we love that with Vault. We don't love that with compute as much. You're going to be finding yourself in a situation where maybe you don't have access to the hardware or the underlying hardware when you need it the most. That's a problem.
Something I wanted to say about time slicing before we get too far past that is that if you're used to the term time slicing when you're thinking about CPU processing, where you're having parallel processing happening, sliced up in equal amounts, and it enforces the actual amount of time that you're using for each process, that's not the case with GPUs. Time slicing with GPUs essentially queues up those different processes so that, yes, it has the order that's all lined up, but if process 1 takes 5 seconds and then process 2 takes 30 minutes, process 3 gets to wait that 30 minutes until process 2 is over. So you want to keep that in mind when you're thinking about time slicing.
And the times are absolutely fictitious because you still have to vend access, you have to revoke access. All of that can be automated, but it still doesn't mean that it doesn't take time. Any time spent on that is time you can be processing documents, doing anything, like building the next multi-million-dollar idea. So of course, simple solution, right? Per team GPU clusters. Your cloud service provider will love that. Your accounting team on the other side might ask you to reconsider your architecture. You got a cluster, I get a cluster. Our teams don't have to interact with each other. It's great, right?
Right.
I see in your case, your GPU nodes are basically doing nothing. It's kind of sad. You don't need that cluster.
But see, in this situation where you have your own cluster per team, you can have your own cluster tied to your own GPUs. So team A, they're not using their GPUs right now. It might actually be at night where they are. They might be on the side of the world where it's at night, and so their GPUs are sitting dormant, which when you think about the cost you just put into that hardware, that's just money sitting there, not being used. Then you look at team B. And team B,
we're actually using the hardware we got, which is good, but we're still not utilizing it 100%, right? We don't want to actually hit 100, but we should at least hit high 90s. Just to make sure we're actually using the hardware we have. And we're not getting that.
Right.
It's not working.
But
so maybe, what if we work together?
Exactly. In this situation, you have multiple teams that are trying to use the same hardware. And so first you set this situation, when you look at tenancy, when you look at the spectrum of tenancy with Kubernetes, you can say, well, on one end of the spectrum, we have those dedicated clusters that each team has its own cluster tied to its own hardware. This is the other end of that spectrum where we have a big shared cluster, and now all the teams are sharing the same cluster, but they're also sharing their hardware. So they're sharing all the GPUs. So those 4 GPUs are now going to be shared across teams A and B, but the Kai scheduler, which is one of the custom schedulers that you can use to help divvy out your processing with your GPUs, it can have those 4 GPUs to be saying, okay, I can divvy out all these requests to these different processors and make it so that I can utilize and make it more efficient.
So it's
However,
like a
there's a
cluster
problem with that.
landlord. It's like a cluster landlord.
Kind of like a cluster landlord, yeah. But
like
what's the
that.
problem with having a big cluster landlord and a big thing like this?
I mean, what I'm seeing here is 4 GPUs that are all less than 50% used.
Okay.
The graph actually has 49% because that's how we drew it.
It's very specific.
That is very specific.
Right.
Which means we're wasting time here because we should be running Unreal Engine on there. Or other stuff that's more important. So maybe we split it differently. How's that?
Well, I think also in that situation where you have all those teams just running in their own namespaces, they can still get in each other's way.
Ooh.
They can get in each other's way because when you think about, I have a team, I have a namespace, but you have a team, you have a namespace, but what happens when you have cluster level resources like CRDs? It's like, well, I want this version of a CRD and you want the other version of the CRD. How are we going to handle that? Because those are at the cluster level.
But yours is outdated, so obviously we're taking mine.
But see, in a situation where we actually meet in the middle of our tenancy,
Yeah, you update and we use my version.
we can use both. We can come together. So vCluster is a tool that allows you to have tenancy inside of your Kubernetes cluster. It essentially puts a control plane inside of a pod so that each tenant, each team has its own API store, its own API server, its own data store, and it has its own cluster that's running inside of this big shared cluster. And then the key here is, if you see that gold or that orange arrow that's going up and down, there's a syncer inside of vCluster that allows you to sync the resources that you approve with that host cluster. But only the ones that you approve. So you can say, well, we're going to share some resources on the host cluster, but then also I'm going to set some resources on that virtual cluster to make it so that I want my own version, which is the version I like, even though it may be outdated, and then you can have your new fancy version.
But say if I'm on my own cluster, I don't want to have to deal with seeing your cluster.
Right.
Because, well, then I need to think about my code differently. I can't reuse code because we can't have the same namespaces. I want to have this.
Exactly. So the user perspective, each tenant sees this. They get their own kube config. So when you are the admin of that shared cluster, you say, hey, here's your kube config of your vCluster. This is where your cluster is. All you see is what you have. You have your own data store, so etcd or SQLite. You have your own API server, your own context, so that you can have your own space that can work with your own hardware.
So it's all isolated.
So it's all isolated.
Okay. Let's talk about isolation a little bit. I think that could be fun.
Yeah.
So because typography doesn't work out, if we make this Kubernetes namespaces provide logical segmentation, we're just saying namespaces. This is a great thing to take a picture of because this is a critical reminder. Namespaces are kind of like folders on your system. They're great to segment stuff, but they don't provide any isolation. This is very important because if somebody messes up namespace 1, you might feel stuff in namespace 2. Now, of course, if we have per team clusters, we get efficiency gains because my team can use more from the cluster. This is supposed to be rotated around. We get efficiency gains because of isolation, but we don't get to fully utilize all the hardware. It's a problem, right? Anytime our GPUs are not fully cracking on, we're wasting time. And we already know, anyone who's an ops engineer, who's ever been an ops engineer, we over-provision hardware anyway. So now add on top of that the cost that GPU hardware is incredibly expensive. This doesn't get much better. Which then, that one rotated in a weird way, but let's go to this one. There we go.
So what we need is we need something that isn't namespaces. We need something that isn't dedicated clusters. Because as you were talking about it, we have dedicated clusters that provide us that isolation, but namespaces provide us that efficiency. We need something that's both efficient and isolated.
I like that.
Right. So let's look at what the next slide shows us. We can have vCluster running inside of a shared host cluster, but then we have our custom scheduler. So we used Kai scheduler before, or you could use any of the other custom schedulers you have for your GPU scheduling, but that's running in your shared host cluster. So you have your isolation, but then you also have your efficiency passing around the workloads that need to happen to hit those GPUs.
The green there looks way better than previously.
Right. That's a lot more than 49%.
It is.
Right.
Can confirm. Because when we drew this, it was more than 49.
Exactly.
Which brings us to a critical question. And you already hinted at that.
Right.
How do you deal with cluster level resources? Like things that are maybe shared between teams without them wanting to share that. I don't know about you, but anytime I build anything hardware-wise, it's manufactured work, right? It's artisanal. We're proud of that. We don't want generally other people to be touching that setup because they don't know, right? We all have those colleagues that just don't know how to work it the same way. I get it. So give me isolation. So we'll pop in a team-specific cluster, and that's going to make life a lot easier. I mean, the first part, of course, if we're talking isolation, and also because you're here, we try to get you in with that, we'll add Vault in the missing space. We want, no matter which operation or option you choose, whether it's a sidecar or anything else, add Vault in there. If there's one thing I want you to take away from this talk is, just like we should be eliminating forever chemicals, we should be eliminating forever credentials, because forever credentials are bad. Unless you like to be in the news for the wrong reasons. Generally speaking, if your credentials don't have a lifetime limit, do something about that. It's a hard problem, right? Quick sidebar, sorry. It's a hard problem. We've got the HashiCorp booth, the HashiCorp zone. Drop by, talk with our solutions folks. We have ideas about that. We've been doing this for a long time. We've learned a lot from our customers. I guarantee you the problems you're facing are problems we've seen before, and we'd love to work on that. Because ultimately, when credentials leak, nobody wins. It is never a nice thing. It is never nice to have to inform your users and do everything. And so you might think, well, it's easy, right? Like in our deployment, we'll pop in the Helm chart, we'll start up our own Vault cluster per team, and we're back to the efficiency problem. Lots of vaults, lots of isolation, but also a lot of hassle. So a Vault per team doesn't really make sense. Instead, we'll use Vault namespacing, because those are not just folders, they are actually logically isolated parts, which enables secure multi-tenancy. And that is a good thing to have. Anytime you don't have to worry about what's happening in namespace 1 affecting namespace 2, that's a good thing. If the namespace is the only thing that changes between teams because you're vending AWS tokens or S3 tokens the same way, including the audio that goes with it, then that's a nice piece of code, because all you have to do is change the namespace in your Terraform code for that Vault config. So you get highly available, which is good. I want my secrets manager and secrets engine and CA and everything that Vault provides to always be available. And isolation, of course, gives us blast radius mitigation. So even could add in team-specific policies. Like, for example, man, the things are popping off there. I guess somebody's getting their tokens revoked. Team-specific policy, right? Our document processing team gets access to S3 in a different way than other people who are just consuming from that. It is very easy to vend an AWS token that is, full read-write for everything. That's a cheap solution. We know this, but we shouldn't. And we have the tools to make this better. So in our case, isolated clusters, isolated namespaces, and we get a setup that's way, way better.
Way better.
So, for example, a policy where team 1 gets access to a GPU cluster for, in this case, 4 hours. And we're back to time slicing in a way where we can add audit logging and everything, and life is good.
Life is great.
Yeah.
When you have all those pieces put together, you have a solution that not only helps keep your teams isolated and efficient, but also secure by having that Vault integration with your cluster.
And so here's the best part. You might go like, well, Vault namespace, I've worked with that. I know I need to set that in the HTTP headers or in the Terraform config if you're using it that way. Yes, you can. But of course, that's also sometimes tricky because teams that consume that might forget about that, right? We're humans. None of us here makes mistakes, but we all have those colleagues that do. It's a hard problem. So instead of doing that, update your Vault config for the Vault server add a change root namespace for a specific listener, and now my team connects to port 8300, and I'm already going to the right namespace. I don't have to think about which namespace I'm in. The team that manages Vault gives that namespace to me. I just connect to the right endpoint. Everything works. I'm in my namespace, and just like with our cluster, I don't know I'm in a specific namespace. I don't need to know. My application doesn't need to know. All I need to know is that this is where I connect to, and it's a lot harder to make mistakes at that point. There's a lot to talk about.
That's a lot. That's a lot.
Which brings us to a couple things that we want to get you to think about a little more,
right.
I think. You want to kick it off?
I think what we want to think about is how we have all these choices to make, but also why we make these choices, why we have them here inside of our architecture and our thought process. For starters, as much as we know and we think that our software is going to be awesome and it's never, ever, ever going to break, does software break all the time?
You
Hardware?
work with the wrong people.
Huh?
You work with the wrong people.
Oh, really?
My stuff never,
Your
no
stuff
issues.
never breaks?
No.
Ah.
Last year at HashiCorp, we fixed the bug live on stage.
Wow.
Yeah. It was my bug.
So obviously HashiCorp software doesn't break.
No software I touch breaks because I architect for failure. It's really simple. Because you know what? Other than just thinking about things that will break and preventing that, what I also like to think about is making sure everything is isolated. If you've ever watched Jurassic Park, you know that isolation is key. Once the raptors are out, you get 2 good movies and then 2 that we don't talk about, and then a 15-year break. But all of that could have been prevented if everything was properly isolated. The thing is, of course, isolation is not just a single layer. You can't just depend on one thing. It's not just network, it's not just a credential, it's not just which peering connections you set up. You need defense in depth, not just because that worked for the Romans a couple thousand years ago, a couple hundred years ago, somewhere in between there, but because it works. Anytime you have layers that you need to go through, somebody else needs to go through those layers as well. And that makes your work easier. It makes it safer. It mitigates blast radius, it provides additional isolation, and most importantly, I think it gives you a system that doesn't add complexity just for the fun of it. It adds complexity that actually adds value. And then clusters. Let's talk about those.
See, with virtual clusters, you were talking about blast radius before. Think about now, if each of your tenants has their own cluster and you have a bad deployment. Who's had bad deployments? Right, exactly. We've all had bad deployments. If you were all in the same big shared cluster and you have a bad deployment going into that cluster, or a misconfiguration, or maybe even that cluster getting compromised because of a, container escape, that's a problem for everyone inside that cluster. If everyone has their own cluster, then it's only contained inside of that one virtual cluster.
You know what I like about clusters?
What's that?
Or any type of virtual setup is that usually the auditing capabilities are way, way better than with a standard setup. And depending on the industry you're in, you have certain obligations that you need to meet. Writing proper logging software and proper auditing software is hard. So get a setup that actually enables you to make these things a little bit easier.
With vCluster, you can actually have 2 layers of auditing, 2 layers of logs. You have the logs that are part of your regular Kubernetes cluster, right? So as a virtual cluster, you'll have all those same logs happening inside of each tenant or each virtual cluster. But then on your host cluster or on your vCluster platform that's managing all of those vClusters, then you also have that logging there. So you can see who and when a vCluster was created or modified, and so you can have multiple layers of that auditing.
And for bonus points, if you want to run your logs through Vault's transit engine or other ways that you want to do it to make sure they are tamper-proof, that's great. Now the thing that I think mostly stood out for us was there's a time when you outgrow your virtual cluster because you can only scale so much, right, within an existing system. But because my code never knew that it was inside a virtual cluster, just like we don't realize we're inside the matrix, we can now shift our code, our deployments, to somewhere else. If you're doing all your Kubernetes deployments through Terraform, these things are, of course, easy. And before you know it, you're on your own H100. H200 if you're unlucky, A100 if you have specific reasons for that hardware.
Right. Now, Kerim, I have to ask you, have you ever tried to upgrade the version of Kubernetes for your cluster?
No, because I use the latest.
Right.
Always.
Right, but your teams may have to upgrade that version. If you're running in virtual clusters, you can run multiple versions of that Kubernetes, of Kubernetes running each of those virtual clusters, so you can say, hey, let's test it out and migrate. So we'll create a virtual cluster, spin that up, run it in the new version of Kubernetes, and then migrate the things over, which makes it nice.
But what do we do about the GPU? What do we do about the GPUs that we have that we now need to get? This is probably a good time to tell you, and Scott thought this was a joke, but it's actually true. If you run IBM Cloud, 50% off on GPUs with the code GPU for you.
50%?
50% is pretty good. Moly. So if you want to go home and do some fun stuff there, try it out. You know, like figure out your deployments. Don't pay full price if you don't have to.
Right.
Because here's the thing. As much as everyone wants to have GPUs, GPU access is a hard problem. GPU fairness is a hard problem. It's an evolving problem. We kind of know that we want to split stuff with others in a fair way, but the tooling is not fully there yet. We've given you some ideas, but I guarantee you, if you look at this a year from now, you're going to have so many more tools that will make your life better. Which really brings us to one last call out. Eliminate forever credentials, please. This is very important.
He agrees.
Yeah.
Yep.
I like it. Commit to not having long-lived credentials. It not only is the right technical move, it will teach you so much about your system. When you get to the point where you have to rebuild your software so it can consume dynamic secrets, you're going to learn so much about your software, about the tools your teams are deploying that you didn't have to think about before because you just always had long-lived credentials. It will make you a better engineer. And if you already know how to do that, teach somebody else on your team because it will make you a better engineer anytime you teach somebody. With that, thank you all. You've been great.